again to the seminar. We have a couple more weeks in the seminar series before the end of the semester. This week we have a PhD student presenting, Ibrahim Abuawad, and he's going to be talking about moisture susceptibility and additives to the binder to prevent that. And if you don't know Ibrahim that well, he went to school in Palestine at Birzeit University, then Jordan University for his master's, and he's been here several years working on his PhD, and says he'll be done soon. So let's welcome Ibrahim.
Thank you, Professor, and welcome all for the weekly seminar. The title of my presentation is The Effects of Anti-Stripping Additives and Modifiers on Illinois Moisture Susceptible Mixes. The outline of my presentation will start with a brief background about moisture damage, followed by the objectives of this study. Then I will display the experimental program plan followed in this study, moving ahead towards the most important part, which is I will show you the results that I got from the laboratory tests, and finishing finally with the main findings. Now, the bond between aggregate and binder is so essential for the durability of asphalt pavement. And this bond can be affected by many factors. One of them happen to be moisture. And moisture can exist and enter pavement through three different transport modes: permeability, suction, and diffusion. Now, whatever is the mean, moisture can damage this bond, leading to the end to what we all know by moisture damage. In other words, moisture damage is the loss of asphalt pavement strength, durability, and stability due to the presence of moisture. Now, the moisture deteriorates asphalt pavement through three main mechanisms: the loss of adhesion bond between aggregate and binder, the loss of cohesion bond within the binder itself, and the aggregate degradation or fracture due to freezing and thawing cycles. We can have one of these mechanisms or more working at the same time in asphalt pavement. Now, in 1930s, engineers started to recognize moisture damage. But it was not until 1960s they started to recognize it as a very serious problem. And the reason of that, the fact that moisture damage, although it is not a pavement distress, but it leads to different distresses. It triggers a lot of pavement distresses, such as rutting, bleeding, fatigue cracking, and raveling. Now, which one of them depends on the aggregate and binder characteristics and the asphalt mixture itself. Moisture alone is not sufficient to create moisture damage. We need another two important factors. We need heavy traffic loadings, and also we need environmental conditions. Fortunately, we have all of these factors working here in Illinois. So this takes us to the objective of this study, which is the determination of long and short-term effects of additives and modifiers when added to two typical moisture susceptible mixes in Illinois, and how they can control the moisture damage. And this objective will be achieved through running several laboratory testing on both the mixture and the component levels, and validating the results we get from the lab tests through running a full-scale accelerated pavement testing. I would like to focus here in this presentation only about the results of the mixture level test, and also some results I got from Atlas. The additives and modifiers that were considered in this study include liquid anti-strip, which was added here in April to the binder. Also, we use hydrated lime added to the aggregate through four different techniques: the marination technique, the slurry technique, and also the wet and the dry methods. Also, two modifiers were used: the SPS and the polyphosphoric acid, which was already mixed with binder, bumping its PG from 64-22 to 70-22. Here is a flow chart which shows the mixture level test that we use in this study. We have three tests. We have the modified H2 test with 5 freezing and thawing cycles. We have the wheel tracking test, and also we have the fracture test using SCB samples. let's talk about the two mixes that we have adopted in this study. Two mixes, we adopted them from a District 5. They were known to be moisture susceptible mixes, N70 and N90. Both of them share 3 aggregate stockpiles, 2 coarse CM11 and CM16, and 1 fine, which is FM20. N70, in addition to that, uses another fine aggregate, which is natural sand, FM02. The binder used for those control mixes is PG64-22, except as mentioned earlier in the case of PP and SPS, where that PG was bumped to 70-22. So immediately after importing the aggregate stockpiles, we measured the absorption values, we measured the aggregate gradation, the bulk specific gravity, and the rodded and loose unit weights. Introduced all of these values in a Bailey method Excel sheet, determined several trials. For each trial, we have measured the volumetrics, the VMA, and air voids, until we reached to a trial which was the nearest one to the target volumetrics, and then we applied the binder optimization concept, as you all know, and came up with the final mix designs for N70 and N90. In this slide, here is the N70 final mix design. The target volumetrics was 13% for the VMA and 4% for the air voids. Here are the aggregate blend percentages, which required 4.9 asphalt content. Similar for the case of N90, the only difference is the target VMA was 13.8. Here is the final mix design. Here's the aggregate blend percentages with 5.2 asphalt content. The next step was to check whether these mixes were moisture susceptible or not. And in order to do that, we ran the Illinois modified ASHTO test, where we only conditioned the wet set samples, putting them for 24 hours in a 60 degrees water bath, then taking them and placing them in for 2 hours in a 25 degrees water bath prior to testing. The dry set samples were only placed for 2 hours in a 25 degrees water bath before testing. And according to Illinois specification, if the TSR value that we obtain is less than 85%, it is a moisture susceptible mix. Other than that, it is not. So as we can see for the N70 mix, the TSR value was 84%, so it is a moisture susceptible mix. In the case of N90, the TSR was 81.9, so also again, it is a moisture susceptible mix. Here we look at 2 wet samples from N70 and N90. We can see the severe sipping rate. It can be counted as 3.3. So also another proof that those mixtures are, again, moisture susceptible. From now on, the conditioning of the wet set samples in the case of when we ran the modified ASHTO test will be 5 freezing thawing cycle. And those 5 freezing and thawing cycles were done in the following sequence. First, we determined the volumetrics, the air voids of the wet set samples. We fill the air voids of the wet samples. We fill 70 to 80% of their air voids with water using under pressure. Then we wrap the wet set samples with saran wrap, place them in a plastic bag, add to them 10 milliliters of water, placing them in the freezer at -18 for minimum 16 hours, taking them out, putting them in hot water, 60 degrees hot water for 24 hours. Repeating those last 3 steps another 4 times will give us 5 freezing and thawing cycles. After the last 24 hours in the 60 degrees water bath, we take the samples, put them for 2 hours in a 25 degrees water bath, and then we go ahead and test them. The dry set samples, we did not apply any change to them, so we only placed them similar to the Illinois modified test for 2 hours at the 25 degrees water bath, and then we test them. We'll talk about here the lime addition techniques that we use. Here we have the slurry method. In the slurry method, we batched each aggregate stockpile in a separate pan. Then we added water to the aggregates, taking it to the SSD condition. Then we add the slurry. Slurry is a combination of water and lime. The water is 3% of the dry weight of aggregate. Then we put that mixture in the oven at 230 degrees until we get rid of the excess water, and then we increase the temperature of the oven to the mixing temperature, which is 295 for at least 2 hours, and then we continue with the normal mixing and compaction process. For the marination, similarly, we start as the slurry method. We batch each aggregate stockpile in a separate pan. We add water until it reaches to the SSD condition. We add then the slurry, similar to the slurry method. And then We place it for 24 hours for the lime to marinate with the aggregates. Immediately the next day, we put that mixture in the oven at the mixing temperature for 2 hours and then continue normally. The wet method, we batch all of the aggregates together in one pan. We add the water necessary to take it to the SSD condition, then add the lime, and then put it in the oven at 230 degrees until we get rid of the excess water. Increase the temperature to 295 for 2 hours, continue with the mixing and compaction. Similarly, the dry method, we batch all of the aggregates in one pan. We put it in the oven for 2 hours at 295. Then we take it out, add the lime, bring it back, put it back in the oven at 295, and then until it reaches the temperature, and then mix again. Another issue we have to resolve before we continue with the mixture level tests is what is the liquid anti-strip content that we need to use with N70 and N90. And in order to answer this question, we adopted 4 liquid anti-stripping contents, 0.25, 0.5, 0.75, and 1%. We mixed those 4 contents with N70 and N90, and then we ran the modified H2 test, meaning conditioning with 5 freezing and thawing cycle. The concept is that the first liquid anti-strip content that provides us with 85% TSR value or above will be adopted and used for that mix. Applying this concept for the case of N70, we have chosen 1% liquid anti-strip, and for the case of N90, we adopted the 0.75% liquid anti-strip. Okay, now moving ahead to the serious part. Here is the results of the N70 mixes from the modified H2 test. We have 8 mixes: the control, liquid anti-strip, PPA, SPS, lime slurry, marination, dry, and wet. And I showed here the 2 thresholds adopted by IDOT. The 60 PSI is the minimum minimum tensile strength for unmodified mixes, and the 80 is the minimum tensile strength for modified mixes. And as we can see, the only mix that passed the threshold for the modified is the SPS, and for the unmodified is the control. SPS, as was expected, provided us with the highest dry tensile strength, while the liquid anti-strip lime did not perform that well for the dry tensile strength. But looking at the wet tensile strength, the liquid anti-strip and lime, especially the lime marination, provided us with very decent results. Looking at the TSR values, control had the lowest TSR value, but when comparing the additive and modifiers all together, PPA had resulted in the lowest TSR value. Now it is obvious that the liquid anti-strip and lime, although they didn't give us a very good dry tensile strength, but they were able to maintain a very good wet tensile strength after the 5 freezing and thawing cycles. The only 2 mixes that passed the 85% threshold were the liquid anti-strip and the lime marination. In the case of N90, we have the same thresholds, of course, here. The control had the lowest TSR value. Again, liquid anti-strip had resulted in the highest TSR value. The lime did not pass the threshold, but still the same. They have the best wet tensile strength with the lime, meaning that they also maintain a very good tensile strength after the 5 freezing and thawing cycles. SPS had the highest dry tensile strength again in this case. But it did not pass the threshold for the N90. So the summary of this test, the control had the lowest TSR value. SPS had the highest dry tensile strength. Liquid anti-strip provided us with the highest TSR value. But the PPA, when comparing the additives and modifiers altogether, it had the lowest TSR value. The lime, in the case of N70 and N90, best tensile strength for the conditioned samples. For the N90, comparing the lime techniques altogether, there was no significant difference. But in the case of N70, no significant difference between the marination and the slurry alone and the dry and the wet methods alone. The next test, which was the wheel tracking test. Here is the, we ran this test on top of asphalt mixes submerged in 50 degrees water. and we ran it with 20,000 cycles. The failing criteria is 12.5 millimeters at 10,000 cycles for PG64-22 or softer, and at 15,000 cycles for PG70-22. So here are the results for all the N70 mixes. And as you can see, the blue line shows the 12.5 millimeter threshold. The first red line is at 10,000 cycles. The second one at the 15,000 cycle. Now, any mix with PG64-22 that is lower than this intersection point, falls below this intersection point, it failed the rating criteria. Any mix with PG70-22 that falls below this intersection point is also failed the rating criteria. Applying this concept, the only mix that failed the rating criteria is the PPA, since it is PG70-22 and it falls way beyond this intersection point. SPS and lime generally, especially lime marination, provided us with the best rating resistance. PPA and liquid anti-strip did not improve that much the rating resistance. Similarly, for the N90 mixes, same concept, same idea. The PPA was the only mix, again, to fail to pass the rating criteria. Liquid anti-strip and PPA also did not improve so much the rating resistance. Again, SPS and lime marination had the best rating performance. So as a summary for this test, all of the mixes passed the rating threshold or the rating criteria, except for the case of PPA mixes in N70 and N90. The SPS and lime marination showed us the best rating resistance, while the liquid anti-strip and PPA had the worst rating resistance. But in general, the hydrated lime techniques, all of them altogether, improved the rating resistance when compared to the control mix. The last test is the SCB test. Here is only figures show how we prepare the SCB sample, starting from the gyratory sample until we have the semicircular bending shape. Here's a typical result. We have this curve between the load and CMOD. The area underneath this curve shows give us the fracture energy. The higher the fracture energy, the higher the resistance to low temperature cracking. This is the main concept of this test. And here are the results for all the N70 mixes. After the detailed discussion and looking at different studies, we came up with a threshold of 600 joules per meter square. And as we can see, when compared to control, all of the additives and modifiers, when added, they increased or not significantly increased the fracture energy. The highest fracture energy was provided by liquid anti-strip, followed by the lime marination and lime wet, and then the SPS. But the PPA and lime slurry and dry did not improve that much the fracture energy. And the -12. Sorry, it's at -12 C. For the case of N90 mixes, all of them, on the contrary, reduced or not significantly even have any effect on the fracture energy when compared to control, except in the case of lime marination and lime wet. PPA had the most significant reduction in fracture energy when compared to the control mix. But most of them passed the threshold. So the summary, in the case of N70, the liquid anti-strip and the SPS and lime marination and wet methods, they all improved the fracture energy. The liquid anti-strip had the highest value. The PPA resulted in no significant improvements when compared to the control mix. N90, lime marination and lime wet, the best improvement on fracture energy, but the liquid anti-strip and lime dry, no significant whatsoever on the fracture energy, but PPA resulted in the most significant reduction in the fracture energy when compared to the control. This takes us to the accelerated pavement testing that we are running right now. The existing pavement that we had our new overlay on top of it, it was continuously enforced concrete pavement with a length of 500 feet and 12.5 feet wide. The new overlay was of a thickness of 2.25 inches. And since we have 7 mixes. Each mix will have 71 feet length and 12.5 feet wide. The tag coat used was SS1HP, applied at 0.04 gallons per yard square at a residual. The asphalt concrete mixes, as I said, we have 7 mixes. We have the control mix, we have the liquid anti-strip mix, we have the hydrated lime mix, foam binder with liquid anti-strip, we have the SPS, and also we have the PPA mixes. Here is just a picture showing the Atlas with the environmental chamber. This is from outside, this is from inside. We can see the heaters, we can see the wet, the moisture that we need always to have while we are running this test. So, as I mentioned earlier, 7 sections, 2.25 inches thickness, 71 feet long, 28 feet. From those 78 were the loading area that we were interested in. The configuration and the location of the loading, we are using the double tire assembly at 110 tire pressure. For the first 30,000 cycles, we are using 10 kips, 14 kips for the next 30,000 cycles, so total 60,000 cycles. But I will show you that we have ran more than that, more than 60,000 cycles. The loading is 4 feet from the pavement edge, and the speed of Atlas is 8 miles per hour. The condition, wet surface, always, and the temperature is 90 Fahrenheit, 2 inches below the surface. Here is a typical loading section, 71 feet. Those are the 28 that we are interested in. Here is the schematic for all of the 7 mixes lying beside each other, starting from the control, finishing with the PPA mixture. Here are the results from SPS section. Line 1 and line 2. Those 2 lines fall in the 28 feet loading area. And as you can see, there is no significant rutting. And we have here the profile from 16,000 cycles, 30, 45, and 60,000 cycles. Similar in the case for line 2. Going to PPA, we start to see some rutting, but it's still not significant. It's only 2 to 3 millimeters maximum. As you can see, the double tire shape is so obvious on this figure. When moving the Atlas to the formed sections, here we have the formed section. We have run so far to 210,000 cycles. 210,000 cycles. Of course, as I mentioned, the first 30 was 10 kips. The second 30 was 14. Beyond the 60, we have increased the load to 18 kips, and still no rutting. Similar for the second line for the foam section, 210,000 cycles, and still also no rutting. This is the foam with liquid anti-strip sections. We have run only 90,000 cycles, and still also no significant rutting whatsoever seen so far. Now the main findings of this study so far: the SPS and liquid anti-strip and the lime have shown good control for moisture damage. The SPS improved the dry tensile strength and also reduced the rutting potential. Again, also the lime have similar trend to improve the rutting resistance. PPA did not improve the moisture resistance when looking at the TSR values and also at the rutting values from the wheel track test. Liquid anti-strip and lime in general enhanced and increased the fracture energy when compared to the control mix, showing us the ability that those two can reduce thermal cracking when used in the field. And at the end, no significant rutting so far from the Atlas testing. I would like at the end to acknowledge the Illinois Center for Transportation, the Illinois Department of Transportation for their funding, the Federal Highway Administration. Also, I would like to thank Bill Pine for his valuable help, especially in the mixed design stage, the TRP members, and of course, Jim for his unforgettable and tremendous help in the lab. And with that, I would like to thank you all for your attention and would like be more than happy to take any of your questions. Thank you so much. Oh, not that much.
Any questions?
Well, I missed the beginning, Ibrahim. What's PPA again?
It's polyphosphoric acid. It's a liquid mineral polymer, which is used as a modifier in general to add when added to binder. And for some types of binder, it pumps the high temperature part, and for some other binders, it pumps both the high and the low temperature parts of the PG. And it is, I mean, generally not used to control moisture damage, but we would like to use it for this study and see how it performs as a, to see polyphosphoric acid.
What's the main use for PPA?
PPA, the main use when they came up with PPA is to reduce the aging rate of asphalt mixtures, to minimize the low temperature cracking. So when you use PPA, it does not age as quick as other mixes.
So it retards the oxidation process?
Exactly. Supposedly.
In your project, you have two different big design, N90 and N70.
Yes.
Right. Between two different design, you also have one mixture has natural sand
Yes.
design, other ones.
Yes.
Besides, and also if you have different compaction design, compaction number, you have different binder content as well.
Yes.
Right. In that case, if you have different type of aggregate inside, mainly the bonding between the aggregate and binder will have something moisture damage
Yes.
on the different entities, right? But I don't know. Do you have any idea of what this mixture A is the moisture susceptibility is mainly affected by either which one, the different aggregate or the binder content? So the two different variables. One is from the adhesive, another one is cohesive.
Yes, we have the adhesive failure and we have the cohesive failure. And those two factors that you have mentioned, theoretically, both of them affect the moisture damage. We need to look at the type of aggregate that we are using, and also we need to look at the type of and amount of binder that we are using. Excess binder can lead to moisture damage. Also, less amount of binder will lead to moisture damage, can lead to moisture damage. But as we all know, from asphalt material, the also aggregate types also can play a big role in having moisture damage, because there are some types of aggregates like silicate, or we have the limestone. Both of them behave differently when mixed with binder, and especially the most important factor when moisture is introduced, because some of them likes water pretty much than the other. So we need to look at those two variables, and hopefully I will look at those two variables in more details when I go ahead and start doing my component test, because I'm going to test the binder and the aggregates, and there will be a new concept that is now used a lot for the moisture damage, which is looking at the surface free energy of both of those components. Try to come with a new concept that we can predict even without doing those laboratory testing, all of this hard work, and try to say at the beginning that, okay, it's good to have those two, this binder and this aggregate can be mixed together, and they will work so good even with the existence of moisture.
I have two questions actually. The first one is, in the very beginning, you said that moisture damage is related to aggregate degradation, like when you were defining cohesive failure and adhesive failure. The third point, I think, was aggregate. How is moisture damage related to aggregate degradation?
When you have water penetrates in asphalt pavement, and that water freeze and goes under with freezing and thawing, contract and expand, it can break the aggregates, resulting at the end in stripping and separation of the asphalt pavement.
Yeah, so that means moisture damage is causing aggregate degradation, not the other way around, right? Aggregate degradation is not causing.
I think, you are right. I think I said that the mechanisms of moisture working inside asphalt pavement leads it works using following those three mechanisms.
Okay.
It can make an adhesion loss between aggregate and binder. It can sometimes, within the binder itself, separate the binder when the binder cannot stand the effect of moisture, and it also can degrade the aggregates.
Okay. And the second question is, why was the fracture energy increased for one and decreased for the other when you add the adhesives?
Let's look at each one of them
The
because
N70 you said the fracture energy is increased, and N90 you saw some decrease, right?
yes, you are right.
Do,
Yeah.
do you have a, I mean,
Some of them did not even change, and some of them increased for, and most of them increased for the case of N70.
but N90
And 90,
decreased.
almost, yeah, and vice versa. Almost, some of them did not change, and some of them, actually, 3 mixes only decreased, and the only 2 have passed the control mix.
Is there a reason for that?
What was the binder content there?
Binder content,
Are they
5.2.
the same?
Yeah, 5.2 for N90 and 4.9 for N70. We did not change the binder content. We kept always the same aggregate structure and same binder content. We did not change that variable in order to catch the effect of those additives and modifiers.
You have different binder content for two different.
Yeah, that, for instance, yeah. I mean, I'm talking about each mix alone.
Yeah.
When comparing those additives and modifiers for each mix, the binder content is the same, the aggregate structure is the same, so that we can only take, capture the effect of those additives and modifiers for the case of N70 alone and for the case of N90 alone. Now, why did that happen? The only thing that I can come up with is the effect of the aggregate gradation and the binder interaction together, because this is the only variable between N70 and N90.
But the actual physical binder content has to make a difference.
Yeah, I mean, for each mix, if you're talking about the mix itself.
Yeah, they're not the same exact mix.
No. N70 and 90 completely different. Yeah,
So this one, I assume, has higher binder content? Or-
and 90, yes.
Yeah. I mean, some of them went up. I don't know why the other ones went down.
Mm.
These weren't conditioned though.
2 hours at minus 12 only.
Yeah, there was no moisture.
No.
I'm curious why you think this is going to somehow indicate any type of moisture susceptibility.
The fracture energy.
Yeah.
And because we need to look at the low temperature cracking for Illinois, because we have this problem so much. So we don't want to end having or choosing an additive or modifier which resolves the moisture susceptibility of the mix, but at the end, increase the tendency of having low temperature cracking in the field.
So this isn't really an indicator for moisture susceptibility so much.
Not directly.
Okay.
Yeah.
I got
Could
it.
it be compaction?
90 gyrations to 70 gyrations, but I cannot remove that effect. Yeah.
Maybe if you had on your graphs, you had the asphalt content, and then for each specimen, you'd probably want to put your density or something. Right. That way we can read that.
Okay.
Because it'd be, maybe there's something there, maybe there's not, I don't know.
Okay.
I'm curious why you don't, in general, I've seen moisture tests, but no one ever measures permeability or anything of that sort. Is there a reason for that, for asphalt?
For asphalt pavement,
Yeah.
nobody measures the permeability.
I mean,
or
you said the
unrelated
mechanism of getting in is suction or
diffusion and
diffusion,
permeability.
but yeah, I mean, obviously you can have water in the aggregate still, but why don't you measure permeability? Because that kind of tells you about the connectivity of the pores.
I think we should. Yes, I think that's a very important thing that we need to measure for any asphalt pavement that we are going to lie in the field. Yes.
'Cause you could test that then at different stages after
Yes.
these processes. You could at least check to see if there's any
Absolutely.
greater connectivity between
Absolutely.
pores.
I agree. Professor.
I think for the first question,
Fracture.
about the SPS and the SPS. The SPS does improve the binder at high temperature, but that doesn't mean that it can give you a better fracture energy at lower temperature. So it depends on what kind of polymer you are using and the impact at that specific temperature. So it's very, very voids that you have in the asphalt concrete is completely different than what you have in Portland cement concrete, and it's usually larger. And the stripping mechanism, it's mostly happening when the moisture is inside the aggregate and trying to push the asphalt or find a pinhole in the asphalt, which putting the asphalt, the aggregate, and trying to walk its way between the binder and the aggregate. But it's not because it is filling the voids in the mix itself, because usually you have a path for the water to move when it's freezing. But when it's inside the aggregate, something maybe Ibrahim he forgot to mention is some of these moistures is in the aggregate when you coat this aggregate with asphalt, because when you heat the aggregate for just a few seconds, like 30 seconds, you're not getting all the moisture out. So some of it just even gets inside the aggregate, and when you coat it with asphalt and cool down, it starts coming out.
We hopefully, when we heat the aggregates, we assume that we get rid of this moisture, but still, yes, but still we will have at the end, yeah. Yes.
So would you say most of the damage is coming from the moisture from the aggregate inside?
You know, I do believe so myself. I do believe that usually, because when you are heating, I mean, look at it this way. When you get a pile of aggregate sitting there, and it has maybe, and all the quarries, they are measuring the moisture in the piles of the aggregate, and you get maybe 1% moisture, or sometimes even more, depends on what aggregate you're using, and you heat it for 30 seconds, what you have is a shock heat, and all the moisture either evaporate or go inside the aggregate, correct? I mean, entropy here, entropy. So what happens is when you put it with asphalt and cool it down, now this moisture is going to start coming back into the surface of the aggregate, right? And with the pressure that you're getting from loading tires, or if you have also still water in the voids and so on. So it's not a very simple mechanism.
That makes sense from a stripping perspective.
Of course.
Are you saying warm mix not a good idea?
Huh? Actually, I did not say that, because the warm mix is a little different. When you are heating your aggregate, you are heating it beyond boiling temperature. So if you are getting your water out, you are getting it out. But also, if you are putting some moisture in the binder to get the foam, you are getting less than 1% of the binder itself. And when it's breaks, it breaks outside. Even if it breaks inside, that's very, very, very tiny amount. I mean, it's 1 or 0.5% of the binder, which is 5% of your whole mix. When I was talking before, 1% moisture, it was of the aggregate, so there's no comparison.
So the warm mix, they actually heat the aggregate to the same temperature?
Yes. I mean, the mix is at a lower temperature. You lower the temperature of your mix, but the aggregate is heated at the same temperature. Yeah. I mean, when you heat the aggregate, we know that we are saying 300 degrees, but actually, in the plant itself, you have a shock of high temperature of 600 degrees Fahrenheit, but it goes the temperature like this. So you have this big wave at 600 degrees that is just for a few seconds, and then it's cooled down. So the temperature is like half of this, what do you call it? The barrel. Yeah, the mixing barrel. It will be at that time around 300 or 310, whatever.
Any other questions? Comments? Okay, thanks, Ibrahim.
Welcome.